Okay, so let's get started. Today is a really cool class. Today we're gonna focus on 2D modeling. It's gonna be a super simple 2D geometry, but we are gonna focus on two really important things. Which one is stress concentration, which in this particular case that we are gonna analyze today is for a hole, which is a really small hole. And whenever we make that hole like really small, like infinitesimal size, that's how fracture mechanics starts. Like that's how a crack starts propagating, and then everything starts cracking within a body. So it's a really cool class to see where like the basis of fracture mechanics, and then we are gonna see the effects of mesh refinement, right? Because if you have a really coarse mesh, it's super simple to mesh and it solves something, right? And then you see some colors, but the fact that Abaqus is giving you a solution doesn't mean that necessarily that the answer is correct, all right? And that today we are gonna check that on how to perform a really good mesh refinement strategy for this simple problem, but you can extrapolate what we are gonna cover here for your particular projects. Before you guys leave, please come here and sign. Attendance is not mandatory, right? But if at some point you need something, I make sure to check these pages before, okay? What else? Let's start, okay? So this is the problem that we are gonna discuss today. It's called a hole in an infinite plate. Yeah. Yes. Yeah, sorry about that. It was my first time using that tool, so if you need me to record that video again, I will do it. I don't think I need to do that because it's really similar to trusses. The only difference is how to import, like how to add the cross section of the beam. Other than that, it's a really similar video. But if you guys need me to record it again, I can. So for today, we're gonna cover this problem, which is called a hole in an infinite plate. So let's suppose a body, right? Super wide and super tall, like we're infinite, right? And then somewhere in the middle of that body, we have this hole, right? We are applying an external stress, which in our case is gonna be this sigma infinite. And based on theory that I'm gonna cover today, if someone is interested in how do they get these 3 sigma here, I can give you that material. But basically what this is saying is, okay, due to the presence of this hole, the stress here, right here at the tip of this hole, or here at the radius along the horizontal direction, is exactly 3 sigma. So it's exactly 3 times the stress that you applied in there. This is more or less like a contour, similar to like CFD, computational fluid dynamics. So basically you have a stream or you have a stress and it's supposed to be homogeneous, right? But whenever we add that hole, it's causing a distortion, if we want to call it like that, and that distortion causes the stress to rise. You guys can imagine that if we make this hole a radius of 0.0000 really small, that's basically the same thing as having a crack, right? And whenever we have a crack, we know that the stress on that crack is more than it is supposed to be without the presence of the crack, and that is what causes the crack to propagate within the body, all right? So, because we cannot model an infinite plate, right? We are gonna model a finite plate, right? We have a width, we have a height, and then we have a diameter for this hole, all right? What this is gonna take is like the stress distribution is not gonna be as smooth, right? It's not gonna be as perfect as we will want it. However, if we make a sufficiently small circle and the width here of this width is sufficiently large, then we can get to that analytical value of 3.0, right? Here is the stress concentration of that hole. However, as we increase d, which is the diameter of this circle with respect to the width, you guys can see how this starts decreasing, right? And that's basically saying, hey, the flow is not as smooth anymore. You told me that this was the solution for an infinite plate, but this doesn't seem infinite, right? This is really finite. And then here's how we take those finite width effects here. Because we are gonna model a finite plate, we're gonna check these values. Sigma norm, which if we didn't have the hole, sigma norm is equal to what? To sigma infinite, right? To the remote stress that we are applying. And here is an approximate solution for what the stress intensity factor is gonna be here at our hole, all right? Not a lot of theory, I just want to cover a little bit of the basis of what we are gonna do today. So we have a basic understanding here. Let's check, all right? So we're gonna have fun modeling here. It's gonna be super simple. So it's remote stress of 100 megapascals. The width and the height, they are both 100 millimeters, and the diameter of the hole is equal to 2 millimeters. If we replace those values here in these equations, sigma norm and KT, we are supposed to get 102 megapascals for sigma norm, and the stress intensity factor is 2.993, really close to the analytical value. And the reason for that is that we have a plate that is 100 millimeters, and then we have a hole that is 2 millimeters. So it's relatively what we can say like a hole in an infinite body. Like the hole doesn't feel the effects of that plate being cut, all right? So let's do it, all right? So we're gonna model this, we're gonna check our solution, and then we're gonna see some meshing strategies on how to improve the mesh for this particular example. So first things first, I already created a folder here. I'm gonna copy the location of that folder, and then I'm gonna open Abaqus. Okay, so file, set work directory, and then I'm gonna paste my folder over there. Let's create a part, all right? So we're gonna create that plate in here. So let's create, I'm gonna call it plate, all right? It's gonna be 2D, and the approximate size is 200. That's gonna work for us in here. So I'm gonna create a rectangle here. So if I click the rectangle, first is asking for the starting corner. So it's gonna ask for the opposite corners as it is showing in here. It's gonna ask for this corner and then this corner in here. So my first corner is -100 in X and -100 in Y. Oh, so it's actually 200. Sorry about that. 200. Let's do it with 100. Doesn't matter. So let's do -50, -50 in X and Y, and then my second corner is the opposite, which is 50,50. If I zoom out, I can check that the width of this plate is 100, and the height of this plate is also 100. Questions so far? How I created that rectangle? No. Okay. The circle. So if I click the circle, what is the center? So it's going to be 0,0, and the diameter is going to be 2 millimeters. So that means that my radius is 1, right? So the second point for my circle is going to be 1,0. All right. So if I check this circle, you guys can see that the radius is 1. So everything seems correct. If I zoom out, look how small and tiny that circle is with respect to this with a plate, right? If we were to assume that that circle is infinitesimal, right? That means that like if you were doing a derivative, so it's something that we cannot measure. That's how the basic theory for fracture mechanics starts. So we're covering here some advanced material, but it's fun and easy to understand. Questions with a sketch? No? Really simple, right? Okay. Materials. Whatever material we use, the solution is going to hold, right? We didn't see any elastic modulus or Poisson's ratio in the solution, right? So it doesn't matter what material we use. So here, let's do Poisson's Young's modulus 210 e to the 3. So steel 210 e to the 3 and Poisson's ratio 0.3. Okay, we have to create a section. The section is going to be homogeneous and it's going to be assigned with the material number 1 that we just created. Am I going too fast? Okay. Then we assign the section. So let's assign the section. Let's do it here. And it's going to be for all of these, it's going to be with that material. So everything is in now this green color. That means that everything within that menu, it's fine. All right. Next thing, always remember to read these left 3. If you get lost, this is going to let you know which one is the next step, which in our case is going to be the assembly. So what we are going to do is bring this plate into the assembly. All right. So we have that plate already into the assembly. Steps. All right. Let's create a step here. And it's going to be static and general. Some of you guys are doing thermal analysis, right? Some of you are interested in doing some heat transfer here. I'm going to cover that if I have time by the end of this class. So it's really relevant for everyone because it's super nice to do some heat transfer here. And if not, I do it next class. Yeah.
I was doing like some ANSYS tutorials, and heat transfer in there is really easy.
It's the same thing. The only difference here is that we do coupled temperature displacement. That's the only difference, right? You just have to check that your elements are temperature compatible, right? Because some elements are for deformation only, and some other elements are for heat transfer only, and some elements are for both of them. They can take into account deformation due to stresses and the deformation due to the heat expansion coefficient, right? So that's the only additional step that we have to really do. And the boundary conditions, right? If you have adiabatic boundary conditions, if you have convection, if you had conduction, and things like that. But let's cover that next after we finish this example. So basic step, static and general, all right? We don't mess with this menu. And let's see, what's next? Let's go to the mesh, all right? So I'm gonna go here to mesh, and I'm gonna create the simplest mesh I can. So I'm not even gonna look at what presets I have, I'm just gonna mesh, all right? So I'm gonna go here to part, and I'm gonna mesh it. That's the mesh that Abaqus has for default for me, all right? One thing I'm gonna do is to check the element type. So I'm gonna go here, and I'm gonna make sure that I'm under plane strain. All right. So I go here to this SAR menu that I don't know what it means. I select everything, and then I go and check what the element type is. All right. For a more accurate solution, we can go to full integration. So integration is that Abaqus internally, it's computing the area of each element. So for that, we need to do an integral. So reduced integration means that Abaqus is taking less steps to compute the area. So it's a more approximate area, thus the results are not as accurate. But if we have full integration, the results tend to be more accurate. That's not always the case. But for our cases, let's go with full integration. It doesn't really add any complication to our problem. Plane strain, I said. Questions? Everything is gonna be recorded, so if I go a little bit fast on the menus, you can always go back. Yes?
Sorry, where did you make that menu pop up?
Yes, SAR. Let's search what SAR means. I'm curious. I don't know. I can check later. But basically what this menu allows you is to select the element type, right? Which is what I was saying before with respect to thermal analysis. Here you have to check that your element is thermal, all right? All right, so that's the mesh Abaqus gave us, all right? I didn't do any special seeds or the special partitions or anything like that. I'm gonna go with it. So the next thing that I'm gonna do is to add deloads, right? So I'm gonna go here and I'm gonna apply, which type of load do I have to apply here or to select in order to apply that stress?
Shell edge load.
Shell edge load, I'm not sure that works.
Pressure.
That might work, but pressure is the right answer. So I'm gonna select pressure, and then I'm gonna select this surface, and by holding shift, I also select the bottom surface. I'm gonna select both of them, right? Because they both have the same stress applied here. So I'm gonna select that. What do I have to put in here? 100 or negative 100? Negative 100. A positive pressure, what is a pressure? Is compacting your element, right? So if you say that your pressure is negative, that means that it's trying to expand or to elongate your sample in this case. Abaqus gives us the arrows, right? So that's always really useful. So if we see the arrows, then we can see that we apply the pressure correctly. All right. Boundary conditions. We have to fix. So if some of you are doing stresses or like this type of analysis and you're getting errors, probably the reason why is because of this. Is we have to fix some nodes in here in order for Abaqus to give us a solution. So everything that is happening in the y direction, we have a load applied in the y direction. But what have we said to Abaqus about the x direction? Nothing, right? So we have to at least fix 1 degree of freedom in a single node. Otherwise, Abaqus is not gonna give us the solution. So what I always do is that I select this point in here. I always select the bottom left corner. And then I say, hey, that particular point cannot move in X. Because imagine, this becomes very unstable. So we apply this load, but it could be here or here. We don't say anything about X. So by fixing 1 point that is not gonna affect the solution, then we explicitly say, hey, stay here and then apply this structure to the plate. Does that make sense? All right. And just to be safe, let's also say that the rotation is equal to 0. Sometimes it rotates, sometimes it doesn't. No, I don't know why. All right. So are we missing something? I don't think so. So let's create a job and let's call it, yeah, job number 1. And let's run it. Submit. Remember, before we leaving, signing this for those who arrived a little bit late. All right, completed. Let's check the results. It rotated. Am I doing something wrong? No. Let me check what boundary conditions I added. Just give me 1 second. I'm gonna select this one instead. I just wanna see if it's because of that one that I selected. Okay, I'm running again. I don't understand why this is happening. Okay, let me try one more time. Let me delete the rotation. All right. I think it's messing.
It didn't work.
It didn't work.
What if you do an edge that doesn't move?
It has to move. I swear I did this problem before coming here and it worked fine. But
Can you do it on the center point of the hole? Okay. Fix that max.
all right. It's rotating. I'll get back to you, but the fact that it's rotating doesn't affect the solution. All right. So what we're gonna do here is check the stress in the 2-2 direction, right? Because we are pulling in sigma YY, right? That's definitely this remote stress that we are applying here. So I'm gonna go here to primary, and I'm gonna check the stress, which is this S, and I'm gonna check S22, okay? And then I'm gonna go and see what the stress in this node is, all right? By the color, I know that is somewhere around 153.9, all right? How can I know the exact value? I'm gonna go here to options, to tools. Then I go to query, and I'm gonna check or select that says probe values. And I'm gonna go here to nodes, and then I can select the node in which I want to know the answer. So I'm gonna select this node in here. And it told me, okay, the stress in that node is 150 megapascals. Is it close to 300? Right, because if we apply the remote stress of 100, the stress here has to be around 3 times that. So are we close? No, we are way, way off. And the reason for that is that basically this mesh is useless, all right? It's a really, really, really bad mesh. So I'm gonna go back, remesh with a second strategy, okay? And then see what the answer is for that particular case, okay? So let's go back to mesh. And what I'm gonna do here is that now instead of having an approximate size of 5, let's go, I don't know, let's go to 1. So 5 times more elements. So let's delete the mesh and let's mesh it again. All right, way more elements, right? We have a lot of elements here in this region, and the circle looks a little bit more like a circle, but actually this is not a circle, right? Look how many elements we have in there. We have 1, 2, 3, 4, 5, 6, 7. What is no, we have 8. We have an hexagon, right? Octagon. Hexagon is 6, yeah. So we have an octagon in here. So that's way far from being a circle. And that's the reason why the results are still not that good. Let's check for this case, all right? So I'm gonna go here and I'm gonna create a new job with that new mesh, and I'm gonna run it. So let's submit that one. Okay, let's check. So for that one, let's check sigma 22. So sigma 22. Let's check what this value is. So options, no, sorry, tools, query, probe values, and let's check what this is. It's 166. So it's still not good, all right? That meshing strategy added a lot of elements, but the solution didn't improve at all, right? And the reason for that is that we are not being smart in our refinement, okay? These elements here in this region are doing nothing, right? Because it's an easy field to solve. Basically, you're just being pulled in the y direction, so you're not doing anything, or adding more elements in that section doesn't really add any benefit to the solution. Where we have to do some smart meshing is here in the circle, that right now is an octagon, right? So let's delete that mesh. So you guys know that if this has a black arrow here, that means that we have more menus behind it. So behind that icon. So if I hold this, I then have four more, or like actually four total icons under this one. So we have mesh part, we have mesh region, then we have delete mesh, and then delete mesh by parts. So actually I'm gonna use this one, which is delete mesh. So I'm just gonna delete it, all right? We are back to square one. So for the global seed, I'm still gonna use 5, all right? It looks like a big element size. It actually is, but for the outer region, we don't really care what the element size is. So where the complication is rising or occurring is here in our circle. So what I'm gonna do here is select this tool that is called seed edges. So I'm gonna select this one. I'm gonna say, hey, for that circle, I want at least, let's go small, 20 elements. All right, so you can either say the element size, or easier, in my opinion, is just say a number of elements. So I want 20 elements in there, all right? And let's click OK. Now we can go back to this menu and mesh the part again. Now the mesh is looking better, right? Here in the outer part where nothing is going on, we have big elements. But where things are getting complicated because of the presence of this circle, we added more elements, right? And then this is starting to look more than like a circle, all right? Let me try to fix this boundary condition. It's bothering me a lot. Yeah, I think we have to fix X and Y. Let me think. Yeah, let's try with this. And let's create a new job. So let's create a job that is gonna be job number 3. And let's submit it. If this doesn't work, I know how to fix it. But it's weird, I've never done that. Okay, let's check the results. Okay, that rotated a lot. Let me fix that. So this boundary condition is only 1 and the rotation. And what I'm gonna do is I'm gonna create another boundary condition. And I'm gonna say that all of the nodes, they cannot rotate. All right, I'm just fixing the rotation in here. And let's rerun this again. I go here and then I just select everything. Let me do it again. So let me delete this. I'm gonna create another boundary condition, displacement rotation, and then I select all the nodes, and then I say that the rotation is 0 for those. Let's submit that job, and let's check what our S22 value is.
Figure out what the SAR is. It's actually S4R.
S4R?
Yeah, and it's a type of element.
Oh, okay.
It's like their naming convention is like letter, number, and
Oh, wow. I always thought it was an A.
it looks like an A.
Yeah. All right. Way better. Okay. Do you guys think we are going to be closer to our solution? Let's check. So let's go to S22. And let's check what this value here is. So tools, query, probe values, and for nodes. And let's check what the stress here is. It's around 186. Way low. We're not getting anywhere with these meshes. So if we really want to compute and be close to the analytical solution, we really have to be aggressive in the meshing of this circle, all right? So let's really be aggressive. So let's select the circle, and let's say that instead of having 20 elements, let's add 200 elements. And let's mesh. Okay. Way different, right? Like there's a lot going on that circle. I don't like that mesh. 200 to 300, whatever you want. It's just for the purpose of getting closer. But this doesn't look that like a publishable mesh. Like if you want to publish this in an article, it's not really a beautiful looking mesh. But I think it's gonna get the job done, or at least get us closer. So let's create a new job. And let's run it again. Who from here is doing 3D in the project? Okay. I think we have time today to do a little bit of 3D. So let's check the results. Results. It rotated again. All right, doesn't matter. Let's check Sigma 22. So let's go here. And for that node, which I don't know where the node is right now, it's around 274, right? Sorry, 278. Like you guys can see that we have a 278 in here. I can actually make that edit, viewport annotations, trial, or color, let's select white. And the font size, let's do it 24. No, let's do it 14. Okay. So this red region is around 278. Really good. I think we have a really small relative error. Let's compute that what the error is. So I like my friend Wolfram Alpha to do some online calculations. So if we want to see the percentage of error, is the difference between my analytical solution, which is 300, minus the solution that I'm getting right now, which is 278, divided by the analytical solution, which is 300. We're getting right now an error of 7.3%. All right, so it's still really good. Let's try to take it under, let's say 1%. All right. So with this mesh, we're not gonna be able to. All right. So let's go here to mesh. We're not gonna be able to do it with this particular mesh. I'm gonna. We have plane stress. Okay, doesn't matter. Let's do a more smart mesh, all right? Let's do a smarter mesh, and let's create some beautiful partitions in here. So I'm gonna delete this mesh, and what I'm gonna do here is to create a partition closer to the circle. So we have basically an outer mesh that is kind of coarse, and then when we are getting closer to the circle or to the hole, then we have a more refined element type. So for that, I'm gonna go here to partition. Partition, previously, we have used it for what? To select two different materials. That's the only use that we've seen so far for partition. But partition is really useful in order to create nice meshes. So I'm just gonna select this tool that says partition face. And what I'm gonna do is to draw a sketch on top of here. So I'm gonna draw a sketch here. I don't care about the size of this too much, but basically I'm just gonna do this one, all right? And that's it. That's the partition that I have. We have an outer circle where we are gonna define some elements, and then we have this circle in here. Actually, let's create a beautiful mesh, all right? let's delete that. So let's go here to mesh, here to features, no. Instances, where is it? I forgot what this is. Parts, plate, features, partition face. Let's delete that one. Let's do the partition again. So I'm gonna create that circle again. And then I'm gonna draw 4 lines. I'm gonna draw, sorry, 2 lines. One vertical line that is cutting everything vertically, and then a horizontal line that is cutting everything horizontally. Okay? That's how it's, we're getting closer. It doesn't make sense right now, but it's gonna make sense in a little bit, what we are trying to achieve here. So, these seeds that I had before, that we said that we had 200 elements in here, let's delete those, all right? So let's delete these seeds in here. Now, I'm gonna select an outer seed. So for everything, let's say that the seed is 2. So here, these outer edges are gonna be meshed with a seed of 2. And then these inner edges, so everything that is right here, let's put something really small. So let's say that these lines that I just highlighted in red, the element size, if the outer is 2, let's make it 100 times smaller, so 0.02. Okay. Let's mesh one small region just to check if this mesh is actually gonna make sense or not. So for that, I hold this icon in here, and I'm gonna select this one that says mesh region. That is used to do like incremental meshing, so small parts by parts. So Abaqus doesn't have the whole control of the meshing part. So let's mesh this one and then see what do we get in here, all right? Let's see. It's gonna take a while because it's a lot of elements. Actually, maybe too much. Maybe I have to decrease it a little bit. Yeah, this is way too much. Let me select less elements. Let's do 0.2. No, let's do 0.1. Let's see with 0.1 how it works. So let's mesh these 4 regions. Now we're talking. This looks really nice. And then we can mesh the outer 4. not too bad. I think it's a really good mesh. So if someone that doesn't know what we are modeling and comes right into the classroom and then sees this and knows about finite element modeling, is gonna say, whatever is happening in the middle, that's where you are interested on knowing everything. Because here in these parts, the stress is not important. It's just basically just a tensile test. So not a lot of things are going on. Whereas in here, close to the radius or to the hole, that's where everything is happening. That's where we are getting the stress concentration. So now let's try and see what the results are for this one. So let's create a new job, job number 5, and let's submit it. In the meantime, let me show you something. All right. Completed. Let's check. So results. See, it is rotating. I don't know why. And let's check sigma 22. It's 282. Let's check what the element or what the value for this one is. So let's go to tools, query, probe values, and let's check for this node what it is. It's 281. So didn't improve a lot. And I think the reason for that is the rotation that we are getting. So let me try to fix it. So all of this is, let me check this. Okay. What is the error that we're getting right now? It's 282. 6%. So not bad. Let's check if this improves the solution a little bit. Results. All right. Sigma 22. All right, yeah, it's 282. So the mesh did a little bit of improvement. Let's try one more time to see if we can get the solution actually a little bit better. So mesh, and let's increase the outer size to 1. All right. So it's gonna say, yeah, I'm gonna do that, but I have to delete the mesh. Okay, that's fine. And let's mesh it again. So I just kept the circle the same, but increased the elements or the element size of the outer like squares that we have in here. Okay. Let's create a new job, job number 6, and let's run it. Okay, let's check results. Now it's not rotating, so we did something good. And it only went to 284. So what did that told us? The outer elements, they don't contribute a lot. So if we really want to improve this solution, let's do it one last time with the elements here like really refined. For your project, don't worry, you don't have to do all of these meshes. Just a sufficiently good mesh. What is a sufficiently good mesh? Just try to do some research. Like if you see beams online, what the element type or the element size they use. If you're doing shape optimization, like if you're doing some analysis of a 2D plate or something like that, then try to look what people usually uses online, all right? Let's do it one more time. So let's go here to mesh. And for these local seeds, we had an element size of, let's check, 0.1. So let's go 0.05, all right? And let's mesh. It's gonna take a while. Okay, let's create a new job number 7, and let's submit it. In the meantime, this is a paper that I published during my PhD, and here what I wanted to show is that in all of these papers, you always do something that is called a mesh convergence analysis, right? So here I'm showing the results if you use this mesh. So the problem, what is the problem? Is this plate that has a crack. So here I'm doing some fracture mechanics analysis. And the only loading that I'm applying here is a thermal field. So here I have a temperature here and in the wall, which is like negative 50 degrees. And then here in the right side, I have a temperature of 50 degrees. And what that is doing is expanding the plate. And that expansion is creating some internal stress inside the plate. That causes a crack to grow. So for your engines are not getting a lot of load. Like there's no one like a lot of loads or stresses due to mechanical loading in your engines. Most of the stresses going on in there are due to thermal loads or thermal cycling. So this is a really important field in here. So what I wanted to show here is that in order to show that my answer was good, I compared my solution against a known solution. And then we can see here that based on the number of elements, the solution actually gets better. Where here 1 means that we don't have any error with respect to the analytical solution. So it's basically a relative error of 0. Where should I have stopped if I was doing this in my regular daily basis? Around this element type or element size, or maybe here in 2000. From there, the solution doesn't get any better, and you're doubling, tripling, or you actually have like 4 times or 20 times the number of elements in here, and the solution is not improving a lot. So that's when I said previous class, you have to refine your mesh, but there's only a certain point where if you keep refining, your solution is not gonna get any better. And that's what we are reaching right now. We have not improved our solution with the mesh refinement a lot. So let's check this solution, results. Let's go here to sigma 22. And surprisingly, 291, all right? So 291. So what is the error if we have here 291? 3% error. That's it, right? For your cases, you don't have known solutions, right? You are just doing an analysis. So what you can do is try your mesh, try to super refine it, and then see if you see some important differences. If you see that the stress changed from 50 to 75 megapascals, that means that your problem is still sensitive to the mesh that you are using, right? here, I think we have reached a point where the problem is insensitive to the mesh. If we keep refining the mesh, the solution is not gonna get a lot better. So we can stop there. But look at the mesh that we have. It's really, 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 really refined. But if we had stopped around like job number 5, that for me was already a really good solution. Okay, so I'm just showing how we deal, those of us that work in modeling, how we deal with these type of problems in our daily basis. All right, cool problem. This is the base for fracture mechanics, believe me. Like from here, the next step is to add a crack, and that crack has a stress intensity factor, and then Abaqus knows what the stress intensity factor for that crack is, and then you can do crack propagation and things like that. So it's really simple, or how we move forward from here to fracture mechanics. For the last 2 sessions, I'm gonna cover a little bit of plasticity, right? So what happens if we have some plastic deformation? Because right now, it doesn't matter how much stress we apply. We always get elastic behavior, right? But probably if we keep increasing this remote stress, that stress concentration near the hole is gonna start yielding that hole. And that's how we get that crack to propagate. So we're gonna cover a little bit of that later in this course. Let's do this problem super quickly in 3D. All right, so let's do the plate in 3D so we get a sense of what the menu or how the menu looks like in 3D. I'm gonna go a little bit fast, but still this is gonna be recorded, so if we get lost at some point, you can always go back to this. So I'm gonna create a new model number 2, and I'm gonna create a new part. So that part is now gonna be 3D. So let's call plate 3D, and that's gonna be fine. So it's deformable and extrusion. All right, so whatever we do, we're gonna extrude it, and it has to be solid. It's not shell anymore. Shell is whenever we are doing 2D modeling, but for now, for 3D, you have to do a 3D extrusion. If you want to model in SolidWorks, make sure that your model is defined correctly whenever you import it into Abaqus. How do we do that? You go here to Model, Edit Attributes, and then here you can see everything about the model. Here we don't have anything because we haven't modeled anything, but that's how you can verify that your model is imported correctly in Abaqus. If you come from SolidWorks and then you try to model in here. So parts, let's create quickly that square. So negative 50, negative 50, and my other corner is 50, 50. Then I have a hole, 0, 0, and then 1, 0. So that we already covered it. All right. So done. My extrusion. This is a thin plate. All right. So let's say that the thickness is 1. So that looks like a thin plate to me. All right. Materials. Let's quickly select any material. So Young's modulus to 10e to the 3. Poisson's ratio, it's equal to 0.3. All right. Let's create a section. Then let's assign the section to everything. Sorry, I'm going a little bit quick, but I want to focus on the important thing. Super different from 2D as of now. Really, it's basically the same. All right, assembly. Let's bring it into the assembly. All right. Steps. Same step, static and general. No difference at all. Okay. Now, here's where the fun begins. Let's go to mesh. So if I want to reproduce the same mesh that I used before, I'm gonna select this. I'm gonna first partition the face, all right? So I'm gonna partition this face. So I'm gonna go here to part. I'm gonna say, hey, I want to use this tool and I want to partition this face. Select an edge or axis that will appear vertical and on the right. Abaqus needs that. Why? I don't know. But it's just to know where you are in terms of creating that partition. So this is my edge that is vertical and on the right, all right? So that's just for Abaqus to create this new sketch on top of our plate. So again, we're gonna select a circle here, and then we are gonna draw this, this vertical and then horizontal line. Okay, so we created the partition. Please pay attention to this. I'm gonna rotate the plate. Is the partition on the back? No, that's the complication of 3D. The partitions, you have to extend them throughout the thickness of the plate. All right?
So if you add a partition on the other side, does that?
No.
Doesn't do it?
You have to select this partition and extend it. It's like I extrude the partition. That's basically what we're gonna do. How you do that? You select this, which is like partition cell. That's how Abaqus calls it. I'm gonna hold it and I'm gonna select the fourth option that is called extrude edges. And that's what we are gonna do. We're gonna select some edges and extrude them along a particular direction. So I'm gonna select this one, and then Abaqus asks us to me, select one or more edges in the same plane. I'm gonna select these edges, so everything, like for those edges that I want to extrude. Is this making sense? I'm just selecting those, like if I were to put a knife and then extend the knife along that edge. The edges must lie in the same plane. Oh, okay, I know what I did. Let's select them again. So this one, 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 this one. Only the outer. Only those. Extrude along direction. So I'm gonna say, hey, no, sorry, extrude along, sweep along edge. So my sweep edge or the extrusion direction, I'm gonna rotate my part a little bit and I'm gonna select this corner in here, right? Because I want to extrude along that direction, which is the thickness. If I select that, Abaqus shows me an arrow and it's saying, I'm gonna extrude those edges that you just selected along that direction, and that's the direction of the extrusion. And then create partition. If I select done, now my plate is also defined like that along the other side. This is the most complicated part of 3D modeling in Abaqus. All right, I've spent days meshing a single part because it's super complicated, like for complicated geometries. All right, if you want to be smart about your meshing, if not, it's fine. All right, what is this hole in here? What happened with that hole? It didn't extrude all the way, right? Let me do it again. So I'm gonna select this 4 lines. And then these 4 lines. And the direction is this one. What? Okay, and then let's do it again for these 4 things. Okay, there we go. So I had to do it slower, like first the lines and then extrude the circle, right? You can see how complicated this becomes. I've dealt with this several times and it still gives me trouble. So I'm human, I know I struggle with Abaqus, right? So don't worry if you struggle with the meshing part as well. So I'm also gonna select this one, extrude this edge, and extrude along direction, and then I select extrude along direction, and then I select this one. All right. So 2 out of 4. Then I'm gonna partition this one. I'm gonna extrude this circle in here and extrude along direction, and then my extrude direction is gonna be this one. Create a partition, and then last cell to partition is this one, and I'm gonna extrude this circle edge along direction, and then I'm gonna select this one. Now everything looks great. We have the 4 regions defined correctly. Okay, quickly, let's add a element size global of 2, and let's create some smart meshing around this region. So same as we did before. So I'm gonna select this, and whenever I'm selecting on that face, I'm also selecting everything, right? Because it's now 3D. So it's not only what you see in front, but also from the back. And for those, by number, let's say that we have 100 elements. I don't want the super accurate solution in here. Let's now go to S4R, this menu here. And the only thing that you have to check in here is that the element size, sorry, the element type is 3D, all right? That's the only thing. Don't mess with all of those things for now, all right? What Abaqus gives you by default, it's supposed to be fine. And let's mesh it. Let's see what kind of mesh we're gonna get. It's taking a long time. Wow. It looks okay. Now the computer is toasted. Yeah, but it's a really good mesh. It looks ugly because of the resolution of the computer, but it's actually a really good mesh. Let's add loads. So now I'm gonna select pressure, and I'm gonna select these surfaces. Sorry, these surfaces. the top and the bottom, right? Those two surfaces are where I'm gonna apply the pressure. And the pressure we said before is gonna be negative 100. Okay? And the last thing is that we are gonna add a boundary condition in this edge. That's how we solve the rotation. And I'm gonna restrict everything in there. So that point is fixed in my model, all right? I know I went a little bit quick, but this is just a brief introduction to the 3D model. So let's create plate 3D. All right, so right, and let's submit. All right, let's let's reduce the element size for this region in here. I didn't know that. Let's do 50.
What's the version beyond academic, professional?
Yeah, so you don't use these computers for professional meshes. Yeah, my meshes are like 5 million, 3 million. So yeah, it makes sense. Submit. What? All right. Yeah, I tried this at home and I didn't have that. So let's make it coarse. It doesn't matter. All right. Let's mesh this again. But you just saw how this number of elements increases in 3D from 2,000 to 100,000 like that, and it's the same problem. So it's good to use 2D. So if you can simplify your problem to 2D, go ahead and do it. Only if even if it's just for a basic understanding of what's going on, and it's not. Oh, come on. I'm gonna select a super simple element type. So linear, wedge, submit. No. I guess I'm not gonna be able, guys, to show you this. Let's do 10. And let's do really small here. Sorry, bigger. No. Just hold on for a second so we can see the results. Let's do 20. All right. If this doesn't do it, there we go. Still, this has 38,000 elements. Imagine doing that by hand. So, like back in the 1979, the solution that I compared my paper against with, like this solution for this, it's a handmade solution, 250 elements. Back in 1979, that's 50 years ago. So it's crazy, the computational power that how we have increased it right now. Yeah, imagine doing the assembly for that by hand. So completed. Let's check the results. Does it look too different? Not really. Let's check sigma 22. 236. So good value. Is it worth display doing it in 3D? No. So when do we do 3D? When your part is 3D, right? Wherein, for example, we are doing cylindrical shapes, like we're doing pipe analysis, like for oil and gas, there's a lot of 3D pipes. So we have to do crack propagation and then see how the oil is penetrating the pipe and how it's breaking it. Fracking, anyone familiar with fracking? So fracking, instead of this being a plate, this is a rock. Then you're adding some fluid pressure and then it's breaking. So this is also when you see a lot of 3D, all right? But I think that for the most of the projects, I think we're clear with 2D, and then we can have an attempt on 3D. All right. If the attempt is unsuccessful, that's fine. But you guys saw me struggle a little bit. It's fine if you struggle, and that's how we learn. All right. Yeah, that's the material that I had for today. Remember, Wednesday, we talk about the project, and I stay here for 20, 30 more minutes solving questions because there's a lot of projects. So yeah, that's how we are gonna do it. Please remember to sign this.